So last class, we talked about two strategies for balancing reacting systems, energy balances, that is. One was the heat of reaction approach. And in this case here, our energy balance, we write it in a specific way just to make things convenient. So this is the extent of reaction I. This is the heat of reaction I at the standard or the reference state, which is 25 degrees C and 1 atmosphere. This is the enthalpy of the stuff flowing out, and this is the enthalpy of the stuff flowing in. Now the key thing here is that our reference is 25 degrees C, 1 bar of pressure, and the molecular species. Yes?
Sorry, I know you just said this, but I was looking down. The first term, what is the
Squiggly guy here is the extent of reaction. I think it's psi. Right, so this is for multiple different reactions. So you can use this approach if you have lots of different reactions going on. Now, the reason why we're doing plus out and minus in, right, is because we've rearranged our equation so that our Q is on the opposite side, right, same way that we did where we had the delta H. Okay, so we're going to go through examples on heat of reaction. And the second approach that we did was heat of formation. Now, I don't recommend the heat of reaction approach, but I'm teaching it just so that you can see kind of the thought process that you've likely already seen before, figuring out how endothermic or how exothermic a particular reaction is. Right? So this is the way that you've probably thought about balancing an energy system, energy balance on a reacting system from like a chemistry class perspective. Now, in the heat of formation method, your reference state is still 25 degrees C, 1 bar pressure, but the atomic species, right? This would be pure oxygen, pure nitrogen, pure carbon, pure sulfur. And in this scenario, the energy balance is quite a bit simpler. We don't have this pesky reaction term. What we've done is we've grabbed this heat of reaction and distributed it across. And recall the heat of reaction at the standard state is equal to the stoichiometric coefficient times by the heat of formation. So what we are doing in transitioning between this approach here, thinking of reactions as endothermic and exothermic, figuring out how many endothermic reactions you have, how many exothermic reactions you have, right? That's really the case that we're doing here in this method. So instead, what we're doing is we're taking this heat of reaction and all the information that's contained within it, and we're grabbing all of these formations and we're dumping them off into the specific enthalpies of either the material flowing in or material flowing out. So it is strictly just an algebraic substitution. If we take this expression here, plug it into this equation, rearrange a little bit, we'll derive this one right here. So we're going to go through examples of each of these two processes so we can see how it actually applies for a system with real numbers and real reactions and all that kind of jazz. Okay. So starting off, let's look at ammonia synthesis, which is a great system to always start off with. For this case here, we're going to say the reaction occurs at 1,000 degrees C and 30 atmospheres pressure, which is going to be similar to the actual industrial conditions for ammonia synthesis. So this reaction here is not quite the formation reaction. Right? The formation reaction creates 1 mole of the product, right? Because we're starting off with atomic nitrogen and atomic hydrogen. So this is very, very nearly the formation reaction, except it's double it. So in this case, the delta H of reaction is equal to 2 times the delta H of formation for ammonia, which in this case is going to be 2 times 46.19, which is 92.4. This is not a particularly favorable reaction to occur. We have a pretty endothermic formation, meaning that ammonia would much rather decompose into hydrogen and nitrogen. So in order to promote the formation of ammonia, we have to heat it up, counteracting the endothermic nature of the reaction, and we have to pressurize it using Le Chatelier's principle to force everything into that direction. And this is why ammonia is going to be a good fertilizer, because it will want to decompose and give off that nitrogen to all the plants so we can eat it. And I want to say, I heard the statistic, and I wish I had reviewed it. I want to say that like half of all the nitrogen in our body is from a chemical plant that produces ammonia, which I thought was kind of neat. All right, so in this one here, we're going to do the heat of reaction method to see how it goes. So what we're going to do is we're going to break it into a couple steps. For this particular process, we're going to assume that everything reacts to completion. So we're just going to use a basis that's exactly the same here. So we're going to say 1 mole of nitrogen, 3 moles of hydrogen, and we can say this is per minute, per hour, per second, or even as a batch. Right? We can just add in the time component if we want as well. And we're going to be making 2 ammonias, and we want to figure out what our heat input or output is going to necessarily be. So, let's look at the heat of reaction method. We have the standard heat of reaction, but we need to figure out enthalpy values for the inlet and the outlet streams. So effectively what we're going to do is break this problem into 3 steps. Bring the reactants down to 25 degrees C and 1 bar of pressure. We're going to perform the reaction at the reference state, right? We have to go through the path where we actually know how much energy is stored in the bonds. And that's why we have to go down to the 25 degrees C. And then the final step, is we heat everything back up. So the nice way about this is really, this is no different than what we've been doing for non-reacting systems, except we're adding in this second step here. But changing the temperature and pressure of a material and figuring out its enthalpy change, that's something we've already been doing for several weeks, or maybe over a month. So, if we look at step 1 in a PT diagram, We are all the way up here at 30 atmospheres, and I'm just going to use and interchange atmospheres and bars right now. We're starting off all the way up here at high temperature and high pressure. We have a delta H associated going from 30 to 1 atmospheres. And we have a delta H going from 1,000 to 25 degrees Celsius. For this one here, if we assume it's an ideal gas, this is actually 0. Right? The enthalpy is not a function of pressure for an ideal gas. For a real fluid at 30 atmospheres, you're definitely going to be a real fluid. This is not going to be 0. But for the purpose of what we're working on, we're going to neglect this contribution. Yes?
If you were working with a substance that was like evaporated at 1,000 degrees and then a liquid at 25, would you have to then take into account like change of state?
Yep, exactly. Which is kind of the same question that I'm trying to get at in problem 4 of the homework. Right? Because the formation reaction for ammonia is a gas at room temperature and pressure, I think. So this formation reaction would be for the gas phase formation of ammonia. But in the homework you have ethylene glycol, which is most certainly a liquid at room temperature and pressure. And I think in the homework you have to figure out an enthalpy value for it at like 400 degrees C or something like that, in which case it's going to be a gas. So yes, if we do have a phase change involved here, we would have to take that into account. But the same procedure holds true, right? In that case, we would depressurize it, cool it to the boiling point, vaporize or condense it in this case, and then cool it back down. So we would have to take into account all those individual steps. So the delta H in this circumstance right here, for all of these processes for any individual component, is just going to be the case of, something we've already seen before. Keeping track of it that way. And so we would have to do this process for the nitrogen and the ammonia. Right, so I just want everyone to get the flow of what's going on. Step 2, the reaction. In this case, it's relatively straightforward. It's just direct application of that formula there. So it would just be the delta H for the reaction step would be the extent of reaction times by the heat of reaction. So in this problem here, what is my extent of reaction if everything goes to completion? It's 2. And then the third step in the heat of reaction approach is bringing everything back up and going the opposite way. So if we have our PT diagram, we're going from 1 to 30 atmospheres, 25 to 1,000 degrees Celsius. We have a delta H associated with the temperature change, and we have a delta H associated with the pressure change. We neglect this in this particular class, but in Thermo 2, that is the whole point of Thermo 2, is to figure out this contribution here. And our delta H would be for ammonia. Now, if you didn't have some material reacting, in this particular example, it's isothermal, so you could just completely neglect it. So everything that doesn't react doesn't contribute. In this one here. But there's a lot of conditional things that are kind of tricky and annoying with the heat of reaction approach. But this is the way that we would think about it if it was a simple, one stream flowing in, one stream flowing out, same temperature coming in, same temperature coming out, and the only thing that's changing is the reaction. So this is kind of just a way to unpack what we mean by an endothermic or exothermic process. Yes?
So that delta H value for your first step would be for, you'd have to do that for both the N2 and the H2.
Correct. Yep. So when we put this all together, erase this business here. Unless you guys want to learn about statics and strengths of materials.
No.
You guys have to take that class anymore? Nope. Oh, I do.
Plus the energy.
So you guys don't know how to select an I-beam that can hold up a particular sized, I don't know, flagpole or something?
Do we need to?
What's that?
Do we ever need to?
Yeah, I certainly haven't used my statics very much at all in my chemical engineering career. So, in this case then, our delta H that we would plug in to our energy balance to figure out our Q. We have our contribution from nitrogen. So the one thing that I did here is I kind of did this a little bit backwards compared to the reference state that we have. Because if we're doing, yeah, I made this more confusing than it has to be. So in this case, our H hat equals 0 at 25 degrees C in 1 atmosphere. So if I'm going from the reference state to my actual condition, then I would be going from 1 atmosphere to 30 and from 25 to 1,000. So that's why this should be a negative, like it is in that equation. But I did the opposite approach. So it actually all works out algebraically, but I just realized that my example problem is opposite of what the problem is here. But the case holds true. The same thought process is what we're actually doing. We're actually cooling everything down to the reference state, reacting it, and heating it back up. But based on how we define the reference state here, I've got the pluses and minuses switched around. Only for the feed. For the outlet, it's exactly the same. I did it right for the outlet. For the nitrogen, or sorry, the hydrogen is the same thing, right? Enthalpy associated with pressure changes, enthalpy associated with temperature changes. Okay, so the only difference, right, just to clarify so everyone's on the same page, between what I wrote here and this expression here, I have plus out and minus in. Here I've put plus, 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 plus. In this circumstance, for the ammonia, we're going from the reference state of 1 atmosphere and 25 degrees C to 30 and 1,000. In this case, I've got opposite. I'm going to the reference state as opposed to from the reference state. So if I switched these limits, when you switch the limits on an integral, you change from positive to negative. So that would be the only difference between the strictly mathematical expression here and whatever. But the concept holds true. Right? I'm choosing a pathway to perform my process, going through bits of information that I know. So just as we had to go through heats of vaporization at the normal boiling point because that's where someone had measured the heat of vaporization, we have to go through the reaction at the standard state or the reference state of 25 degrees C because that's where someone has measured the heat of reaction. So it's the same concept of vaporization except we're changing chemical bonding structures. Any questions with the heat of reaction method? But the procedure, right, follows here. Cool down the products. I mean, you could heat it up, but most of the time you're doing reactions at a higher temperature than 25 degrees C. Cool everything down, react, heat everything back up. Now, if you have a different inlet and outlet temperature, then that would, of course, just change your limits of the integration. You can have a different inlet and outlet pressure. It would just change your limits of integration. Yes?
Sorry, so say you were doing H2O, and you start out at 1,000 degrees, so you'd have to cool it down to its boiling point then?
Well, so for water, water is nice and convenient because we actually have the heat of formation for both gas water and liquid water.
So say if you didn't.
If you didn't, then yes. So in the case of, let's say, ethylene glycol for the homework,
Okay.
right? They don't have the heat of formation for vapor ethylene glycol and liquid ethylene glycol. So if that were the case, in this cooling down step, at some point you would be condensing to a liquid, and you have to add in
Phase change.
delta H of vaporization.
Gotcha.
And depending on the direction that you're going, things can get a little bit confusing. Should it be a positive delta H or a negative delta H? In this way that I've drawn it here, it would actually be a negative delta H of vaporization because you'd be getting energy out.
Okay.
But if you were to go this direction, because here we're going from gas to a liquid, which is the opposite of what the heat of vaporization is. The heat of vaporization is how much energy does it take to go from a liquid to a gas. But if I choose a path that goes the opposite direction, that's the negative heat of vaporization, or you could think of it as like the heat of condensation. Right? Boiling something is endothermic, condensing it is exothermic.
Okay. And then, sorry, so just to clarify,
Mhm.
so then you would start at that boiling temperature, and then you would do the integral of that back down to the reference state, which is 25 degrees.
Yes, so you would go,
imagine-
so let's say in this case we would depressurize the system. Let's say we're a gas at high temperature now. I would cool it down until it becomes a saturated vapor. I would condense it, have to keep track of that energy associated with the phase change. And then I would have to continue to cool the liquid down to 25 degrees C. So we would just add in that one extra step, but it makes it a bit more complicated because then you have both the liquid and the vapor heat capacities. But in this case here, right, of course, I covered up the reaction, but you know, ammonia, hydrogen, nitrogen, they're all gas phase at room temperature.
So, sorry, so
Yes.
just, so on the homework then, so for like the problems where it's like Cl2, you have that reference state go to 0. Now does that have to do with the heat of formation then?
For Cl2, so okay, this is a good point to bring up. So this is for question 2, I think you're talking about?
So, yeah.
Okay, so this is a good clarification question. What is the heat of formation of nitrogen and hydrogen? 0. They are at the reference state. Chlorine, Cl2, is at the reference state.
Gotcha.
Because the pure atomic species of only chlorine is gaseous chlorine. Bromine is liquid bromine. Fluorine is gaseous fluorine. So if you're creating nitrogen, hydrogen, oxygen, those are all at the reference state. And so in those circumstances, you don't have any heat of formation or anything like that. Okay. Now, next example, heat of formation. So we'll do a different reaction with slightly different conditions to highlight the strengths of the heat of formation approach. So this is actually, coincidentally, I wrote these notes years ago. But it's actually formaldehyde synthesis. But from a different pathway. In this way, it's methane, not methanol. So we're going to feed stoichiometric amounts as well. So 1 mole, half a mole, 1 mole, 1 mole. But in this case, the feed is going to be at 50 degrees C, and the pressure is 5 bar. Leaving the system, it's going to be 150 degrees C, because this is an exothermic process. Well, it is with methanol. I don't actually know what it is on this one here. And the pressure, let's just say, is 5 bar as well. Now, in the heat of formation method, which is what we're going to be doing here, the reference state is the atomic species. Our energy balance is given right there. What we do in the heat of formation approach is we'll build a table. where we have all of our species, CH4, O2, formaldehyde, and hydrogen gas. We're going to have material flowing in. It's going to have some enthalpy in, material flowing out, and enthalpy out. Let's fill in our material balance. 1, 1/2. We're going to say that nothing is coming in for those. Nothing is coming out. We have 100% conversion. And there we go. So we don't have to worry about those ones or these ones. So we just have to come up with numbers that we can fill into this table, which is what we're asking for in the homework assignment. Right, in homework number 4, I'm asking you to give me the number for whatever the species that you're interested in. It could be ethylene glycol at 400. I think it was solid carbon dioxide, and I don't remember the other one. Liquid chlorine, I think, basically what it was. Because it was at 200 atmospheres. So if it's a gas at that pressure, I'd be impressed. Okay, so we just need to fill in these values here. So the heat of formation approach is really nice because it is the same formula for every single species in the system. For this particular one, because they're all gases. The boiling point of formaldehyde is about, I want to say it's minus 20 Celsius. So all of these are gases. For every single species, the enthalpy formula in this particular problem is going to be exactly the same. You are going to follow these steps. First, you're going to create the compound following the formation reaction. In the case of methane, that means you're going to take solid carbon, gaseous hydrogen, and you are going to create methane at 25 degrees C and 1 bar pressure. So you're going to make it at 25 degrees C and 1 bar. Step 2, we are going to heat it up. But that temperature is going to change whether or not it's coming in or out of the system. This is the enthalpy for heating. And lastly, we're going to pressurize. If we were, however, doing a different reaction where one of these was a liquid at the standard state, or we didn't have the heat of vaporization for that compound going into the vapor phase, we would have to potentially choose a slightly different pathway here. That question.
So we're pressurizing from the standard state to our 5 bar?
Correct.
We're not pressurizing from in the
No. In the heat of formation approach, we don't care what goes on in the process. All we are doing is we are just stopping every molecule that enters, asks how much energy do you have, and we stop every molecule that leaves, and we ask them how much energy do you have. And then the imbalance of those energy levels is our Q that we are solving for. In the heat of formation approach, we don't care if any individual reaction is endothermic, any individual reaction is exothermic, doesn't matter. All we care about is how much comes in and how much goes out. So it's important to recognize that in the heat of reaction approach, you're actually forced to go through and think about how the different reactions contribute, or how they might change as a function of temperature. So there is value in looking at what the different heat of reactions are and how they change as a function of temperature or process conditions. Right? Because if you have one endothermic and one exothermic, you're going to be promoting one or the other if you're changing the temperature of the conditions. Temperature of the reactor. In the heat of formation, we don't care. It's like an atom balance, kind of. We don't care what reactions happened. All we care about is where are the hydrogens, where are the carbons. In the heat of formation approach, we're just keeping track of the energy coming in and energy coming out. So there could be 100 reactions going on. And this is why a process flow simulator that's generally written is going to be written to handle this type of a process. Because there could be multiple reactions going on. And especially if you're dealing with something really complex like crude oil, you don't know what reactions are going on. There's no way you can know. So you just keep track of what's coming in and out. Yeah.
So the components are coming in at a greater heat and pressure, but I don't see that taken into account.
Right, so in this case here, so if we're going into the system, so coming in, so the T coming in is going to be 50 degrees C, and that'll impact this term here in this contribution. Leaving, it will be 150 degrees C.
Oh, so the H hat you have up there is just the in and
For
not-
all of them. This is for in and out.
Oh,
So I would apply this equation here for the methane, for the oxygen, for the formaldehyde, and for the hydrogen gas. It's the same equation for all of them. The only difference is what is the temperature that I plug in, potentially what is the pressure that I plug in. But for this particular problem, they're all gas phase, so the only thing that's changing is the temperature. Yes?
And are we ignoring the pressure term again?
We are.
So step 3 is just not a.
Yeah, we're going to go on this one.
Is that how it is on the homework too?
Yeah. Well, so for the liquid one, no. So for a gas, for an ideal gas, strictly speaking, this is no approximations. An ideal gas, well, other than obviously all the ideal gas approximations. But for an ideal gas, the enthalpy is not a function of pressure. For a liquid, it is. So for the liquid, we have delta PV is how we keep track of the pressure change enthalpy. So that's specifically what I was looking for in that problem. Because it's 200 atmospheres, which is clearly high enough to be a relatively significant contribution to the enthalpy for pressure changes.
Sorry, how do you keep track of it for a liquid?
So delta H for a liquid going from P1 to P2 is going to be delta PV. So, well, I mean, fluid should be integral PV, but well, I'll just delta PV out, so let's make it easier. For the approximation that everyone I expect to probably use would be this. Let's just talk about that one there, as opposed to getting into the details of PDV or VDP. Let's just keep it this way.
Okay.
But this is what I would expect. And here, this assumes that it's incompressible, so that V hat is equal to a constant. So it's the same density. If you assume the density is the same, then you get the pressure term here. We haven't focused on this too much on the exams, but we've touched on it throughout the semester so far. All right, so I highly recommend heat of formation approach for most all of the circumstances that we're going to be doing in the class. It's simple, it's algorithmic, there's no trickery, we don't care how, so as long as you can do the material balance, then the energy balance is just a sort of a busy work tacked on top of it. The only tricky part associated with any of these methods is keeping track of the pathway that you have to do going from your reference state to whatever the temperature, pressure, and phase of the reaction that's going on. If this was a liquid phase reaction, we would have to be creating with the heat of formation the liquid, and we'd have to be heating and cooling the liquid. If you're a material that you look up the heat of formation, for most materials, they only have one number for it. For really commonly synthesized materials, you can have a heat of formation of the liquid or heat of formation of the vapor. The only difference between those two is the vaporization energy, how much it takes to go from the liquid to the vapor state. But the only difficult part in all of this is keeping track of this step. What is your reference state and how do you transform or calculate the enthalpy changes of temperature, pressure changes, and phase changes. But the concept is exactly the same as what we were talking about with flash balance energy balances. So flash separator energy balances. Right, we chose a reference state. I recommended choosing the liquid, but you could also choose an arbitrary reference state. Right, we're going from the reference to whatever the final conditions are through a series of steps and pathways. And then you just basically plug it into here, and it's exactly like we would have done for a normal energy balance for non-reacting system. Okay, any questions? All right. So please look at the project. Come to class prepared on Friday with questions so we can get them out of the way as soon as possible, and I can kind of try and help go over and set up the problems.